Thank you to the organizers for putting together this lovely event. And let me also use this opportunity to say all the best to Bill. I think I first met Bill just after I finished my PhD at a conference. I knew who he was because I had read his Dirichlet space survey, so it was very nice to meet the man. And I was really amazed by how welcoming he was. So, I was this newcomer to the community, and he really welcomed me with open arms. And I quickly realized that he was a great person to interact with and to hang out with. So thank you, Bill, for being so welcoming and just for being an all-around great guy. All right. So I'm going to talk about von Neumann's inequality in several variables. And probably I don't need to spend a lot of time talking about the classical stuff, but I still feel like I ought to give at least a perfunctory treatment of the classical von Neumann inequality. So this was proved by John von Neumann in 1951. And it says that if you take an operator T on a Hilbert space H that has operator norm at most 1, and if you plug it into a polynomial P and you compute the operator norm, then this is at most the sup norm of the polynomial over the disk. Right? So, for all polynomials P. And as many of you know, this is sort of a fundamental connection between operator theory and Hilbert space and a complex analysis on the unit disk. Right? So we have this, this bridge between operator theory and complex analysis. And this was generalized to two variables by Andďo a little later, where he looked at pairs of contractions, but because you want to plug them into ordinary polynomials, you want to assume that they commute. And he looked at the sup norm on the bidisk. And then, at least for the purpose of this inequality, everything works out in the best possible way. This is due to Andďo in 63. So now you have two operators on the same Hilbert space H. You assume that each of them is a contraction. So it's less than or equal to 1. So j equals 1 and 2. And you assume that T1, T2 is the same as T2, T1. And then you are allowed to plug them into polynomials. And what you get is the same thing, basically. So then the norm of P of T1, T2 is at most the sup norm of the polynomial over the bidisk for all polynomials in two variables. And just like in one variable, this gives you a way to go back and forth between operator theory of pairs and complex analysis on the bidisk. Right? And maybe in contrast to the one variable case, now there are actually results in complex analysis on the bidisk whose only known proofs use operator theory. So I mean, in one variable you can sometimes use operator theory to prove complex analysis results, but typically there are other proofs that are purely complex analytic. On the bidisk, I'm thinking of things like the work of Agler and McCarthy on extension sets in the bidisk, or about their work on interpolating sequences for H infinity. Those results actually use the operator theory in a crucial way. Okay, so this was a big success story, and then if you've never seen this, you would say, well, why stop at 2? But of course, as many of you know, this doesn't work for 3 variables. So there are counterexamples. So for d greater than or equal to 3 variables from the 70s, so 1970s. And let me say a few words about these counterexamples because there's a point I'm going to try to make later. So there's a counterexample due to Kaiser and Veropoulos. And what they do is they exhibit 3 commuting 5 by 5 matrices. So 5 by 5 contractions. And later this was modified by John Holbrook to get 4 by 4 actually. So Holbrook. And a polynomial, a homogeneous polynomial of degree 2 in 3 variables. And so the polynomial looks like this. It's x squared plus y squared plus z squared minus twice the mixed terms. And then I think so the cleanest maybe is Holbrook's example, and then he works out that this has sup norm 5 over the tri-disk. But if you plug in his matrices, then you get operator norm 6. And okay, so 6 is bigger than 5. And so the von Neumann inequality in 3 variables doesn't hold in this way. There was also another counterexample by Crabb and Davy. And they have 8 by 8 matrices. And so 8 by 8 matrices. And the polynomial, let me also write it down. It's a degree 3 homogeneous polynomial in 3 variables. And it looks like this. So it's x cubed plus y cubed plus z cubed minus xyz. And so they can realize, with operators, they can realize 4. But you can convince yourself that this has sup norm strictly less than 4. Less than or equal to 4 is easy, and then you can assume if it's attained somewhere, then you get a contradiction. Yeah, so again, this gives a counterexample to von Neumann's inequality. Let me just mention in passing, well, this is, these are very explicit counterexamples, but I think it's fair to say that our understanding of what really goes on is a little lacking. And sort of one thing where you can see that some of these questions are quite tricky is something that was already mentioned by Katalin Badea, namely this question of what the smallest counterexamples are. So there's a 4 by 4 counterexample, and in the other direction, it's not terribly hard to show that 2 by 2 matrices satisfy it, but 3 by 3 was open for a long time, and it was only proved less than 10 years ago by Greg Nees, I think it was 2015. That actually it works for 3 by 3 matrices. So the von Neumann inequality holds for 3 by 3 matrices. And 3 by 3 sounds like it might be an exercise, but it's not. This uses deep results in complex geometry due to Łukasz-Kozinski. Okay, but that's not the question I'm going to talk about. The question I'm going to talk about is whether you can get this with a constant here. So the question is, so suppose D is at least 3, right? So we know everything in 1 and 2 variables, at least for the purposes of this question. And then the question is, does there exist some finite constant CD such that the von Neumann inequality in D variables holds up to this constant CD? Such that the norm of P of T1 through TD is at most the CD times the sup norm over the polydisc. And you want this for all D tuples of commuting contractions. So pairwise commuting, right? Ti, Tj is the same as Tj, Ti. So commuting contractions. And for all polynomials in D variables. Right? So I think that's a very natural question, of course. Once you know that it fails with constant 1, it's very natural to ask if there's some constant that makes this true. Also, I think an answer either way would be interesting. I mean, if the answer is yes to this question, then this will have fairly profound implications. For instance, some of this work I was hinting at in 2 variables, for instance, the characterization of interpolating sequences would just carry over to several variables. The operator theory approaches would still work. And you get a constant in the constant of interpolation, but I think we could live with that. If the answer is no, that could also be interesting because you could ask for sort of extremal operators that make this fail, and they could have some kind of structure. If you ask the analog of this question on the ball, then it fails, but the extremal operators that fail it are the Drury-Avison shift, and you know, that told us a lot about the situation of operator theory on the ball. So you could hope that this does something similar. Okay, so let me say up front, I don't know the answer to this question. So if you came here to learn the answer, then I'm sorry to disappoint. But I can tell you a little bit in this in this neighborhood here. So people who study this question have studied a quantitative version of this, where they say instead of taking all polynomials, you restrict the degree of your polynomials, and then you do get constants, and then you can ask questions about these. So let C, D, comma, N. So D will always be the number of variables, and N will be the degree. So this should be the smallest constant. Such that, well, the usual thing to do is to ask for this inequality for all degree n homogeneous polynomials, so that the norm of P of T1 through Td is at most C d comma n times the sup norm of the polynomial. Okay, so again, for all T1 through Td commuting contractions, and for all P polynomials and D variables that are homogeneous of degree n. Okay. So let me tell you some things that are known about these constants here. So the obvious thing is, of course, so this is only interesting if D is at least 3, right? If D is 1 or D is 2, then all these constants are 1 by von Neumann's inequality and Andå's inequality, respectively. So von Neumann and Andå tell us that C1 comma n is the same as C2 comma n is equal to 1 for all n. Okay, so I'm only going to talk about D at least 3 now. Now this example of Holbrook that I mentioned here, where you had 6 as the operator norm and 5 as the sup norm, shows that this constant C3 comma 2, so 3 variables, degree 2 homogeneous polynomial, is at least 1.2, right? 6 divided by 5. And to my knowledge, the current world record for this is due to Grinspan, Kaluzhny, Verbovetsky, and Hugo Waterman over there, who showed that. So yeah, let me first write the name before I continue here. So Grinspan, Kaluzhny, Verbovetsky, and Hugo Waterman. So in 2013, they showed that C3 comma 2 is at least 1.23. Right? So they have a polynomial that's similar to this one, but they have some parameter here which they optimize over, and then they get this, this lower bound. Okay. Then there's a very nice construction due to Pizier from 2001. And he has a tensor product construction that basically says if you have a counterexample in D1 many variables and another counterexample in D2 many variables, then you can tensor them together to get a counterexample in D1 plus D2 many variables. And if you, he didn't quite phrase it in this way, but if you look in this language, what his construction gives you is that C D1 plus D2, comma N1 plus N2 is at least as big as C D1 N1 times C D2. This is supposed to be 2 N2. Okay. And so because you know that C3, 2 is at least 1.23, it makes sense to iterate this here. So if you iterate this inequality with multiples of 3 here and multiples of 2 here, then you get that in particular C3k, 2k this grows at least like 1.23 to the k, so it goes to infinity exponentially fast. And so this tells you, so these constants c, d, n, they're always at most as big as these constants c, d, right? And so this tells you that if such constants c, d exist at all, then they have to grow exponentially in d. All right. So what about, so these are lower bounds. What about upper bounds? So there's an upper bound of Dixon from 1976, and he showed that C, D, n is at most the complex Grothendieck constant, so this is just some constant, times 3D to the n minus 2 over 2 times 2e to the n. And Dixon also observed that this bound is good if you fix the degree n and let the number of variables go to infinity. So this, so let me just say this is good in this regime if n is fixed and d goes to infinity. So he has a corresponding lower bound where this exponent here is slightly smaller than the lower bound, but the gap is not that big. Okay, so that's a good bound in that regime, but Dixon also acknowledged in his paper that if that's the question you're interested in, so that one up there, then the regime you should be looking at is actually the other one, right? It's the one where d is fixed and n goes to infinity, right? And if you look at that regime, then this Dixon bound is actually exponential in n, right? You can see it here. And it's fairly easy to convince yourself that exponential, you can do better than exponential, right? So let me explain what you can do here. So the goal, what I want to talk about is that, so determine, so what is the behavior of C, D, n for fixed d and you let the degree go to infinity, right? Okay. And yeah, so you can easily do better than exponential when you fix d. So let me explain what I would consider sort of the trivial estimate is. So suppose you have a degree n homogeneous polynomial and you plug your operator in. Well, the most naive thing you can do is you just use the triangle inequality and use Cauchy-Schwarz, right? And so if you do this, so suppose your polynomial looks like this. So I'm using the usual multi-index notation here, z to the alpha, and so d variables and homogeneous of degree n. And then if you plug in some tuple of commuting contractions, like so, then you can use a triangle inequality. And because all of these are contractions, you can estimate this thing against 1. So this is at most this here, right? And then you can use Cauchy-Schwarz, and you have to know how many things you're summing, but that's the dimension of the space of homogeneous polynomials of degree n and d variables. So this is this binomial coefficient d plus n minus 1, choose d minus 1 to the 1/2. So doing Cauchy-Schwarz, and then you had alpha squared. And that's the norm of the polynomial in the Hardy space H2, which of course is at most the soup norm, right? So this is at most d plus n minus 1, choose d minus 1 to the 1/2 times the sup norm of the polynomial. And now if you fix d, then, and you look at this, this binomial coefficient, then you have a product of d minus 1 terms that are roughly like n, and then you take the square root. So this tells you that CD, so this tells you that CDN is controlled by some constant depending on d times n to the d minus 1 over 2, right? And so you get something that grows at most polynomial. Oh yeah, thanks. Thanks, James. Thanks, yeah. All right. Yes. Okay, and then you get this growth here, right? And so my reason for pointing this out is that so this is what I would consider the trivial estimate, and anything you do, you need to measure against this trivial estimate, right? Okay. So the question is, can we do better? And the answer is yes, at least we can do better than this trivial estimate. So that's the first thing I want to mention. So again, all of this is only interesting if d is at least 3. And then what you can show is that CDN is at most some constant depending on d, which is okay, times log n to the d minus 3. So let's say for n at least 2. So you get, not just get polynomial growth, but you get logarithmic growth. But in particular, this is, I think, interesting if d is equal to 3, because then this is a constant. And so this tells you that, so in particular, you get that the sup over all n of C3, n is finite. Now, I hasten to add, this does not mean that von Neumann's inequality in 3 variables holds up to constant, because these constants CDN were defined using homogeneous polynomials, right? So it doesn't tell you that there's a constant. But it tells you that something that I've been trying for a while doesn't work, namely, sort of the one naive approach you could do is you can look at these classical counterexamples, and you realize they're homogeneous polynomials, and then maybe you try to take homogeneous polynomials of higher and higher degree and somehow show that this has to blow up, right? And okay, this is not going to work. You get some finite constant here. So if you want to have counterexamples to this question, you need to do something different, right? So for instance, you could do something like rational inner functions. I think that could be a fruitful place to look at. Let me also point out, so the fact that you get a power of a log here, I mean some power of a log, is maybe not too unexpected to some people. So there is work of Pizier, and some of it is attributed to his PhD student, Dyer. So he explains this Pizier explains this in his book. And they do a different quantitative version of this question. They look at n by n matrices, and then they get some growth that is at most some power of a log in the size of the matrix. And if you sort of do obvious modifications of their arguments to deal with these homogeneous polynomials, then you get that something like CD, n is at most a constant times log n to the d. Okay, so the fact that you get some power of a log is maybe not too unexpected, but yeah, I'm claiming you get d minus 3 here. Okay, good. Now, not every polynomial is homogeneous, right? And so you could ask what happens for non-homogeneous polynomials, or also for more general holomorphic functions. And there's a version of this. So let me explain that. So I need to introduce a little bit of notation to deal with the non-homogeneous case. So first of all, let me define the Schur-Agler norm of a polynomial to be the supremum over all commuting contractions, over all operator norms of commuting contractions. So this is sup of a norm P of t, where t is a d-tuple of commuting contractions. And so the question is, how can we bound the Schur-Agler norm? Well, ideally in terms of the soup norm, but maybe the next best thing we could settle for is in terms of some function theoretic norm that you could compute in examples. And to explain this, I also need to introduce a little bit more notation. So the radial derivative of the polynomial is just the sum zj dp by dzj. And finally, the radial dilation PR is P of Rz as usual. And soup norm always means soup norm over the polydisc now. Okay. And then I can offer some version for non-homogeneous polynomials. And so what it says is the following. So again, we're assuming D is at least 3. That's the interesting case. And then for polynomials, you can do it for holomorphic functions, but I'm just writing it down for polynomials for simplicity. We have that the Schur-Agler norm of the polynomial is at most some constant depending on D, okay, fine, times, okay, the value at the origin, that doesn't hurt us, and then you have this expression here, the integral from 0 to 1, you take the radial derivative of your polynomial, you do the R dilation, you take the soup norm of the polydisc, and then you need to throw in some weight, and the weight is log 1 over 1 minus R to the D minus 3 dr. Okay, so maybe that looks like a mouthful if you've never looked at it. But I think, again, the most interesting case is probably if D is equal to 3. So let's look at D equals 3. Okay, then at least you can forget about the weight here, right? If D is equal to 3, then the weight is 1. And so what this says is you need to somehow take a derivative of your polynomial, and then you need to look at how fast it grows as R goes to 1. So this thing, you take a derivative and you look at the R dilation and then you integrate. This is, at least in one variable, something classical. This Bezoff B0 infinity 1 norm that appeared in Peller's functional calculus for power-bounded operators. And so this is sort of a similar idea here. My point is, okay, this looks complicated, but in principle, it is a function theoretic quantity that's on the right-hand side. And for explicit examples, you could try to estimate this. And actually, Greg Nies was able to estimate this for certain functions that have to. So you can also do this for holomorphic functions. It's the same formula. And then Greg Nies was able to estimate this for certain holomorphic functions that are related to rational inner functions. So you could show that they're in the Schur-Agler class using this kind of formula. So in principle, it is something where you can do analysis on. Okay. Let me also mention that this actually contains this result as a special case. If you work out what this does for homogeneous polynomial, the radial derivative just multiplies by the degree, and the R dilation comes out as R to the n. But I just wanted to formulate this earlier. Okay. Let me also mention that this kind of argument, so there are always constants here, but there are some isometric things you can prove for this kind of argument. Which may be interesting for at least one person in the audience, for Hugo maybe, because it answered a question of his. So there's another thing you can do. So what Grinspan, Kalushny, Verbovetsky, and Wardeman observed is that multiplication by a monomial doesn't have to be isometric on the Schur-Agler class. They showed that there are polynomials so that the Schur-Agler norm of P is strictly bigger than the Schur-Agler norm of, let's say, Z3 times P. And they ask if you can always do this if the Schur-Agler norm of your polynomial is bigger than the soup norm. And the answer is yes. And what you can show is, so again, let's say D is at least 3, then the Schur-Agler norm, so then for all polynomials, the Schur-Agler norm, the infinity norm of your polynomial is the limit as, let's say, m goes to infinity of z3 times zd to the n times p, and then you take the Schreier norm here. And so in particular, if the sup norm of your polynomial is less than the Schreier norm of your polynomial, you can find some monomial so that multiplied the monomial times the polynomial has Schreier norm strictly less than the sup norm. Right? So this was something they asked. Yeah. Okay. Yeah. So in my last few minutes, let me. So I'm not going to give you detailed proofs, but let me explain the basic approach that is behind this, because it's actually a fairly simple one, or you could also say fairly naive approach. And it, the idea is if you want to plug d operators into a polynomial, I mean, the easiest thing you can do is you plug in one at a time, right? You plug in your first operator, then the second one, and so on. And if you think about what this means, after you've plugged in your first operator, what are you left with? You're left with a polynomial in one fewer variables, right, in d minus 1 variables. But your polynomial now has operator coefficients because you already plugged in one operator. So this is some kind of a procedure that you might want to study. And so consider operator value polynomials. And it turns out you don't just want to keep track of the top degree, but also of the bottom degree. So let's say they look like this: z to the k, where these ak are operators now. And then you want to plug in another operator. And the only thing you know about the new operator you plug in is that it commutes with everything you had before. So it commutes with all the AKs. So if T and B of H commutes with each AK, so then you just plug it in. So you take the you define this. Maybe it's not necessary to say for this audience, but this is really the product of operators. It's not a tensor product. It's composition of operators. And then you can ask, well, what kind of inequalities can you prove in this setting? And so let's see. So you define a new constant. Right, this is, you let Kmn be the smallest constant. Such that you have this, the sum k equals m to n, akt to the k is at most the sup, but now you take the sup in one variable of akz to the k for all admissible choices of t and ak. Right? So t should commute with ak, t should be a contraction, and so on. So for all choices. Yeah, it's saying thanks. Yeah, there's no constant. So yeah, k m comma n. Yeah, thanks. Yeah, so for all choices of a, k, and t. And then the goal is to understand these constants k, m, n. And they, so it's actually possible to understand them quite well. So let me just, so I have upper and lower bounds, but let me just tell you the asymptotics that you can get from this. So the asymptotics is that k, so there are two interesting regimes in this case. It's one where the ratio of n over m goes to infinity, and one where it goes to 1. And so the constant is, it behaves approximately like 1 over pi times the logarithm of n divided by m if n over m tends to infinity. And so here we have upper and lower bounds. And if you go to 1, then it tends to 1 if n divided by m tends to 1. And so the second thing is what is behind this isometric result, so this one. And the other thing is what's behind the ones that involve constants. So once you have this, you can try to estimate the Schur-Aglar norm of general polynomials by doing this procedure, by plugging in one at a time. You need to do something more, but maybe in the interest of time, I'm going to gloss over that. But let me finish with remarking something about lower bounds here. So here I'm actually claiming that this is an equivalence. And so to get the lower bound, you need to write down operators that actually give you, that show that this is also greater than or equal to. Right? And so what do these operators look like? The operators that give you the lower bound here, they are, in some sense, old friends. They're these Vogel-Hankel operators that also played an important role in the solution of the Helmholtz problem. So let me just say, so the lower bound over here, so the lower bound is achieved by Vogel-Hankel operators. And so they look like you have a copy of the shift, then you have a Hankel operator, it has some kind of symbol, and then you have a shift on the conjugate Hilbert space. So this is an operator on H2 direct sum H2 bar, let's say. Okay. And if you use operators of this type for the A's and for the T's, then you can show that this has to blow up, and in fact it has to blow up like 1/pi times the logarithm. And so once you have that, then at least to me it seemed natural to take operators of this type and then see what happens for the original von Neumann inequality in D variables, right? But the bad news is, for sort of a totally different reason, operators of this type, once you scale them so that they become contractions, always satisfy von Neumann's inequality. So it's a different reason than this one. But so the maybe slightly disappointing thing was that these operators that give lower bounds in this lemma actually don't tell you anything new about the von Neumann inequality in D variables. So I think we need different examples here. All right, I'll stop here. Thanks.